hit record and my audio looks okay, give a message in the chat if it doesn't work. Alright, so for those in this video and on Discord, you can see my webcam. You'll notice that it looks slightly different, but not really. I'm in the process of moving, so I have everything including my desk all packed up. So yeah, anyway, I don't have a backrest, so I might end up getting a little bit uncomfortable as I'm sitting on my bed right now. But yeah, today will be the last, it says week 5, but it's week 7. This is a combination of week 5 and 7, but I got through as much as I could with the new topic, the TCCs, but I've only managed to cover serviceability design, so not strength design. So I'll give you kind of what I think it's about, but I haven't had a good chance to fully look at it because I've been busy with a bunch of stuff like moving. But yeah, I'll try give you guys as much of a head start as I can. This should help you with your first assignment. I have no idea what the second assignment is about, and this will be the last video that I record and the last session that I host. Yeah, just because of the pace at which everything is being released, Hamid's only releasing week by week, and this is completely new content this year. It wasn't in the course last year. I'm not able to keep up in time, unfortunately, but in the future, maybe next year or something, I might try to finish off this series properly. But for now, in this year, this will be the last video in the last session. Okay, so without further ado, first we're going to start with midterm discussion. So talking a bit about load combos, because I realized I didn't fully cover it properly, and it's still something that you only really touch on it in 2 core subjects, steels and concrete. In steels you cover it for about a week, and then you kind of use it throughout the time. And then concrete, they just assume that you know it, and also in concrete you only deal with the gravity load combinations. Let me just check I'm on the right document. In concrete you only deal with these ones, which in my opinion are pretty straightforward, so nothing to do with the wind cases or anything. So we're going to talk about the wind related cases a bit first, and then we'll talk about what the second half of this term's about, including composite design, timber composite design, and specifically we're going to be looking at timber concrete composites, so that's what we're going to be working towards. And it's going to use a lot of Eurocode, because this stuff is basically non-existent in the Australian codes. So everything's going to be based on Eurocode, where they use a lot more timber over there, and then they use a lot more timber concrete composites over there as well. Okay, cool. So load combinations, right? So basically this is one of the questions in the midterm, and I've just taken a snip from it, and it's like a connection design thing where you have 2 members that are perpendicularly fixed to each other, and connected with this little bracket, and it's screwed in on both sides, and basically the idea is that the loads are going upwards like that. Well, you have to check if the net loads are gonna be acting upwards or downwards like this, and then you have to do a bunch of other stuff, but we're just going to focus on that part. Basically, first thing you have to do is consider this whole system. Basically it said that the trib area, so all the roof sheeting and everything that connected to this, this area was 2.2 meters squared, and then you had everything in kPa. So when you multiply the kPa by the area, which is in meters squared, you get a kilonewton load. So that's what causes the axial / shear loads acting on the connections. So for these connections, correct me if I'm wrong, but type 1 connections were the shear ones. The bracket and the rafter would shear against each other, and try to split that screw in half, whereas these ones here on the top plate and that part of the angle bracket, that's being ripped up, so that's a type 2 screw happening there. So yeah, basically there's going to be some axial load here, and there's going to be some shear load here, right, from the same external forces, right? And the external forces that were acting on it were the roof self-weight and the wind uplift, and you have to consider the load combinations related to this. So basically there's this one, which is dead load only governed, so that's the 0.5 kPa downwards, and you can see just from these numbers that the wind uplift is more significant than that. And I guess the other thing is that because we're talking about withdrawal for type 2 connections, compression in connections doesn't really break them. So if these two members were like so if the bracket was pushing down against the top plate, it doesn't really like the connection doesn't really get destroyed, I guess. So the downwards case would only really put shear into that connection there. Anyway, so really we're focusing on these two. Sorry, I say that, but basically the difference between these two sorry, okay, let me gather my thoughts real quick. So let's look at this blue one, right? So 1.2 G plus W, right? And then there's the Q and like combination factor, but let's just ignore that one for now. And we also have this one, 0.9 G plus, let's just say W, right? So basically, if you think about it like this, there's like a positive direction on the system. Let's just consider the wind uplift as upwards, right? We basically don't have downwards wind pressure, and this is basically downwards like wind in combination with gravity, right? So whenever you use this load case, right, the one which also includes like the combination factor with Q, that's actually just looking at wind acting in conjunction with gravity loads, so like downwards wind pressure. So we actually don't have any downwards wind pressure, right? So really that one's actually just 1.2 G. But this one here is basically wind reversal, right? So if we consider the directions and positive being up, that's wind uplift in our case, like sucking the roof sheeting up and making the whole system want to go upwards like that, right? And gravity is actually beneficial in that case, so you have to subtract, well, I put a negative there, but let's just say whatever value we got, which was 1.1 kilonewtons in this case, we have to add like a negative sign to gravity, because gravity is beneficial for this uplift case, right? Because it's the thing that's holding it down. And you'll see later when we're talking about like the European load combinations as well, that like these numbers are kind of like, you always have basically a reduction factor when you're considering dead load as beneficial, right? So the 0.9 is like beneficial dead load, whereas like the 1.2 is like an exaggerated dead load for when it's detrimental, right? Beneficial dead load, the reason you don't consider 100% of the dead load is because sometimes like less stuff weighing down the system is installed in the worst case scenario of like wind, like say like a 1 in 100 year wind event happens and just pushes like the roof sheeting up. Say that happens at the same time as like all your dead load not being installed yet, then yeah, you're gonna have this like worst case scenario happen. Anyway, so that is just a concept of how to use that how to use that load combination, yeah, and how it kind of applies when you have like upwards wind pressure. Okay, so yeah, that's that. Alright, oh, sorry, I'm gonna check the chat on my phone. I don't have a good setup. I don't have the dual monitors like I did when I wasn't moving. So I'm gonna check chat every now and then by like logging into my phone. I don't think I've seen any questions. Let me just check the audio is still working because I'm paranoid. Yeah, looks like it's still working. Okay, so timber floors, right? You've seen like in the first half of this course that we have like you should be fairly familiar with joist systems. So joist systems are where in red you've got the joists running in one way. Oh, sorry, on the very top you have like your plywood flooring, right? Which is just so that people don't fall through your floor. Basically, you need like a flat surface to walk on, and then so the blue thing flows onto the red thing, and the red thing are the joists, right? And they're running in one direction. And then in the other direction you have your bearers, right, which go into the column. So it's almost like a grid shape. In the middle here I've also added like, sometimes you can add in mid-span blocking or bridging this is like for compression, or not really compression, mainly for like flexural reasons. So if you recall, like there's flexural, what's the word I'm looking for? Restraints, so it doesn't buckle, right? So that mid-span blocking, such bridging, kind of helps with the buckling. Yeah. And it's basically, it's the same as if you've seen the stud walls, right? So you got like your vertical stud members, and you've got like the noggins, which are running horizontal, which restrain it from compressive buckling, right? Similar idea, but now we flip the whole thing on its side. And instead of compression, the joists are taking bending. It's been a long day. It's been a long day. Alright. But yeah, hopefully that makes sense. Okay. That's a typical configuration, the joist system. And like basically now we're moving to the engineered solutions for when we have like longer spans and things like that. So you might see joist systems in like residential housing, in like kind of old smaller buildings. They can be multi-story sort of joist systems, but like, yeah, not like skyscrapers and stuff like that, right? Long span solutions, you've basically got two main types. You've got your panel plate system, so for example like a CLT system, which we've briefly covered earlier in this course. We've talked about a little bit earlier in this course. That's where you've got like this engineered wood product, where you've got planks of wood like next to each other, and you've got different layers stacked perpendicularly to each other, like you can kind of see that. And you've got your major direction and your minor direction, right? So the major direction is the one where you've got more members running that way, and your minor direction is that one where you've got less layers, I should say. In terms of framing, so it's basically, when I say framing, I'm talking about what goes underneath it, right? So you've got your CLT slab, and then you can have beams. They could be glulam beams or like LVL beams or whatever. And depending on where you put them, right, is the direction the forces want to flow, right? So if you've got a beam here and here, for example, then you've got your members spanning that way, so the forces want to flow in one direction. Whereas if you've got maybe your primary beams and your secondary beams like that, the forces have two directions to flow, right? So yeah, that's your different framing options that you've got. Yeah, you want to basically connect the panels so that they're spliced together. So those are two different options that they've presented there. These are straight from the slides. I'm not like an expert on this topic, and I'm kind of just like learning alongside everyone in this course. I'm looking at it for the first time. We don't use like mass timber too much in Australia, so yeah, I'm using this as a learning exercise for myself as well. And then yeah, so floor to support connection. So support could be like a wall or like a column or something, for example. so you can kind of see how, like for an edge support, so like say for example on like here's like a beam, continuous beam, that one might be what that one looks like in reality, and your continuous support could look like either one of these, for example. So yeah, that's like moving away from like just simple free body diagrams. That's what these kind of things look like in real life. Modular cassettes. So I looked it up. I just looked up cassette like define on Google, and I think it's literally based on the shape of a cassette tape, which, I mean, I'm probably a bit older than you guys, but like I don't even know what a fucking cassette tape is, right? But I think it's just the fact that it looks kind of like this, right? Maybe a cassette tape looks something like this. I don't know, but basically this is called a modular cassette, right? It's where you've got multiple webs, and you've got your top flange and your bottom flange, and yeah, these are like prefabricated, so they're just like click and drag and dropped onto site basically. And timber's like relatively light to lift, so yeah, it leads to pretty fast paced construction. Unlike concrete, if you're forming these as like suspended slabs, you don't need to prop it as it's curing. Like prefabricated timber, yeah, you don't have to wait for like concrete to cure to gain like its full strength and stuff. As a suspended slab, so timber's just like a very fast pace kind of, it allows fast paced construction on like multi-story buildings and stuff. So that's one way to use it. And yeah, any questions? I have an eye on the chat, so if you've got any questions, just drop it. Composite action. So composite materials, and this is kind of what Hamid specializes in, and I'm actually surprised that Hamid wasn't on this course earlier, because he's the timber guy, and two, he's the composite guy. And a lot of the stuff he talks about in this course is really fucking advanced. Like, it's not even in the Australian standards yet. Like, we're going to be going off the Eurocode, and this is like freshly researched kind of topics that you guys are going to be looking at, right? Like, this isn't common in industry yet, like in Australia. So it's pretty advanced, I would say. Composites, right, is where you have multiple materials. So here's some examples of composites. We've got TCC, which is timber concrete composites. You have STC, so steel timber composites, right? That's just one example of STCs, but there's others. For example, I did my undergrad thesis on, we had these kind of like reinforced glulam beams, right? So you can reinforce using like steel rebar, or you could use glass fiber rods, or like carbon fiber rods to reinforce your timber planks to have beneficial strength. That's another example of a steel timber composite. But in terms of floors, we're talking about these ones. In TCC, like, if you look this up on Google, they think you're talking about TCC, but what happens is, how I read it is TCCs are like when you combine timber products with other timber products, right? So, for example, the modular cassettes, the prefabricated ones, where you use like, say like CLT as the floor, or the flanges, and then you use glulam, for example, for the webs. I think that's like a TTC. Fuck, I'm getting confused myself. But yeah, we're going to be looking at things like that. In terms of composite action, essentially when you're... So here I've provided an example that doesn't involve timber, right? What's fairly commonly used in industry is steel... common. Yeah, I'm just going to say common. I say this, but I haven't designed anything like this personally myself, but it is relatively common, I believe. Use steel beams and reinforced concrete, and you cast them together. And you need something to basically connect the layers together. So we have something called shear studs, right? Which sounds like really complex but these shear studs are basically just the connections you've already kind of looked at, right? They could be they're basically a dowel. So a dowel is something that like it's basically like a type 1 connection, I guess. So you're doweling the steel section to the reinforced concrete in this case, and you're preventing any slip between the two materials. So you want them to bend, like when they bend, you want them to essentially behave as like a singular gigantic cross section, if that makes sense. So here I've got an example kind of. So I've got this notebook, right? And as I bend this notebook, right? Sorry, on Discord you probably can't see my webcam, but like I've got this little like sketch pad thing. And as you bend the materials, right, you can imagine like the piece of paper like sliding against each other, like that, right? But with the shear studs, so if I like stapled these pages together, like if I stapled down on these pages and then try to do that, there's no like slip between the pages. They're like perfectly bend at the same rate, I guess. So yeah, that's basically how it works. Okay, so building on from that, types of composite action, right? So you got non-composite, so that's like, imagine the piece of paper. So I've got like two pieces of paper and I'm like kind of bending them so it folds down, but there's nothing stopping one piece of paper from shearing against another piece of paper, right? That's basically when you have non-composite action. So that's like this, right? There's no shear studs, and the strain profile looks like this, right? So the bending, there's like two neutral axes, right? There's bending happening here in the middle of that, and then you have bending happening here in the middle of that bottom material, right? When you have a fully composite thing, so that's like, imagine you've got the piece of paper on this sketch pad, and I was just stapled like really frequently, right? You basically have a perfect monolithic cross section, like a gigantic cross section, all acting at once, right? So you've got one neutral axis, right? Now, partially composite, which is what your assignment's going to be, is when you have staples, like going back to this paper and sketch pad like analogy. You have staples, but like infrequently, right? So like to the point where there will be some slip, but they'll also behave like kind of together at the same time. So that's where it gets hard, and that's what we're going to be talking about. Yeah. Keep going. Yeah, so non-composite deflection. This is just like kind of a thought exercise, because I think most of the questions in this course is focusing on number C case, the partially composite case. So for non-composite deflection, what happens is you have some amount of total distributed load, right? Whatever loads, say like people, pedestrian traffic or anything like that, like on top, that's split onto your two elements. So here we're going to be talking about timber, a reinforced concrete slab and a glulam timber beam, right? Based on the stiffness of the materials, the load will be distributed, right? But basically, yeah, that will be like W1 and W2, and all up will be the total distributed load, right? So basically, but overall, if this whole thing deflects that much, right, the thing above it will also deflect that much, right? So we're saying that the deflection of the slab is going to be the same as the deflection of the beam, but they will be sliding against each other, right? So let me just draw that out as if these were like the sections. So there'll be like, you see that? There's like a bit of, they're sliding past each other basically, right? But the deflection is still the same. So uniform distributed load, simply supported beam, these are the deflection formulas, right? Now like how the weight is distributed. Again, it's based on the stiffness, and when I say stiffness, right, here I'm talking about the product of this is like your geometric stiffness, basically, your bending stiffness based on the shape, and this is like your material stiffness, right? So the product of these two things is called the flexural rigidity, right? So basically you're accounting for both the shape and the material of the two things, and you're taking the ratio of that, and that's where that formula comes from. So that's how the load is distributed, right? And yeah, I've just put in, this is like your formula for moment of inertia for your rectangular section. And yeah, you've got material stiffnesses from timber and from concrete. So here I've just provided AS3600, like this is from the concrete code. These are the most common compressive strength mixes for concrete, and then their corresponding material stiffnesses, or like elastic modulus, right? And then for glue lam, those are your values based on your stress grade for the glue lam in the Australian code, right? Now it gets confusing because we're talking about this like we're referring to the Australian code for glue lam, but later when we start doing the stuff you can only do from the Eurocode, we're going to be using the Eurocode glue lam values. Yeah, so fully composite deflection works a little bit differently, right? You use the modular ratio method. So this is basically if you've done concrete, which I think most people have, here's like a reinforced concrete beam. It's concrete. So you've got two materials going on, right? You've got your steel reinforcement, and you've got your concrete, and that's what reinforced concrete is. So reinforced concrete is a composite material, right? And when we're analyzing it for deflection, I'm just going to draw the steel in blue. Basically, when you're doing concrete design, you have to assume that the concrete and the steel strain at the same rate, so they bend at the same rate. So if I was to map on the strain like that, engineers' beam theory says that we have a linear stress distribution, a strain distribution in flexure, in bending, and I can find the values of what your tensile steel and compressive steel are if I follow this line down. Like when I say line, I mean it's like this this line. It's like you can use your what's the word? In like year 8, like linear algebra or whatever. You can follow your rules of like y equals mx plus b, all that, right? So it's a straight line basically, and you can find these values. So basically what I'm trying to say is reinforced concrete is an example of a fully, is it called fully composite? Yeah, a fully composite material, right? We in all our design we assume the steel and concrete have a perfect bond to each other. One thing which contributes to this is the reinforcement is like this deformed bar, which has better like bond properties. So yeah, that like grabs onto the concrete. That's like a bit of a mechanical anchor as it bends. Yeah, cool. So that's basically what we're dealing with, right? And so in the same way that we did it for reinforced concrete, we use the modular ratio method to basically find the deflection in a fully composite beam, right? The reinforced concrete slab in a portion of it, and shit, I'm looking at this now and I realize B1's not always 1,000. Sorry, just take this as B1. Don't take it as 1,000, because it's more about like an effective flange. Here's your effective concrete flange. Okay, I'm gonna fix that on the notes after the video. But yeah, that's not always 1,000. I was thinking of something else. Anyway, yeah. So we've got this basically T-shaped beam, right? And we're dealing with a transform section. So what we do is we apply this there's a number called N, right? Which is a ratio of the material stiffnesses, and you just turn the whole thing into timber, right? I haven't drawn it very well here, but usually this number will be higher, right? It might be like 2. So if I was to draw it to scale, say this was like 3,000 or something. That's not a good number. Say it was like 600. This would be like 1,200, this dimension here, right? If this was about 2, right? So we basically just widened that top flange. And now we can do all our calculations as if it was one material, right? Which is timber. Yeah, so step 1, apply the modular ratio, or find the modular ratio, which is just the ratio of the stiffnesses, right? And that's where you get those values from. Next, you have to find the location of the neutral axis, right? So this is on the transform section. So this is already the one that was like, say like, what did I say? 1,200? Yeah, this was like already 1,200 or something, right? And you find where that average, what's the word for it? You're finding the Y centroid, basically. You're finding the Y centroid. Center of shape, I guess. And then, yep. Step 3, find the transformed moment of inertia. So we've transformed it. It's all timber, right? And now we basically have to sum all these different components together. This is the way that I like to think of it. It helps me because it's like very visual. So you basically create 2 shapes, right? So shape 1 is your concrete flange, which has now been transformed into timber, right? So that's shape 1, and that's where you get inertia 1 from, and that's that component there. The second one is your timber web, so that's just that. Next you have to shift, right? So we've created the shapes, they're at like 0, 0, they're at the origin, right? And now we have to move it, right? So we move it from the neutral axis all the way up to the center of that shape. So that's parallel axis theorem. We shift it upwards, and in doing so we give it more stiffness. So the further up you have to shift, or the further away from the neutral axis you have to shift, the more inertia you get, right? And we do the same thing for the second shape. So from the neutral axis you shift down to the centroid of the timber web. Okay. And then last step, you apply the deflection formula, and this is basically what you've seen. The only difference is you apply, like everything's timber now, so we're using E2, so just the timber modulus, and you apply the moment of inertia you just calculated, and that's how you do it. Okay, so here's where the hard stuff starts, right? Partially composite deflection. So now we're not dealing with something that's fully composite, like how we did it for reinforced concrete, and we're not dealing with something that's basically sliding against each other, right? We're dealing with something in between. So we have to use something called the gamma method, and like it's completely arbitrarily named because it's the same thing as you learned in the last week of steels. We are basically, to recap, if you've done steels. So gamma for steels, right? For AS 4100, and it also is in AS 3600 in the column section, right? In the Australian code, gamma method is basically talking about, well, firstly, it's for columns, right? You have an effective length factor, right? So your effective length is equal to your effective length factor times the length of your column or whatever. But basically, if you want to do a more thorough analysis of what KE is, your effective length factor, basically in reality, you might not have something that's fully rigid or fully pinned. It might be somewhere in between, like 50% in between or something, just ballpark. And it really depends on the stiffness of that connection / shape, and the columns and beams, everything attached to it. And so that's where you launch into the gamma method, which is basically finding the gamma at the top and then the bottom, and then using a graph to find KE, right? So to find exactly how pinned or like rigid that connection is, basically, right? So that's Australian gamma method, right? And gamma is just an arbitrarily chosen Greek letter, right? So when we're talking about gamma method in this course, it's something completely different. It has nothing to do with that gamma, right? So in the Eurocode for timber, in some random appendix, right, in Annex B, gamma method is talking about how partial, I guess, your composite is, right? So 0 means it's non-composite, so sliding against each other when it's bending. 1 means it's fully composite, right? So like reinforced concrete. So anything in between is partially composite, and that's where the gamma method, you have to use it, right? So what the typical method is you calculate either gamma 1 or gamma 2, so that's gamma of material 1 or material 2. So if you've got your T-beam, and that's like RC, and that's timber, we're just referring to 1 and 2 as like element 1, element 2, so the flange and the web, right? So you either calculate gamma for the flange and then set gamma 2, so the timber, to equal 1, or you do it the other way around, so you find gamma for the timber and you set gamma as 1 for the concrete. How they do it in the lectures is they find gamma for the concrete and then they set the timber's gamma to 1, right? So that's a method, and we'll come back to this. And then basically, okay, it's weird, right? So when we're talking about fully composite, okay, wait, go back even further. When we're talking about non-composite deflection, we basically had two neutral axes, right? So one in the middle of the timber that was bending, and one in the middle, other way around. One in the middle of the concrete that was bending, and one in the middle of the timber, right? When we have our fully composite deflection, you basically have a neutral axis for this monolithic cross section, right? So you've got one neutral axis. So basically, what the gamma method does, because the real strain is more like that first thing, that the real strain is probably more like the non-composite one, but we're using the gamma method to basically pretend that it behaves like a monolithic cross section, if that makes sense. So we're not calculating the real location to the neutral axis, but like a effective location to the neutral axis, where it kind of is like in between those two methods, if that makes sense. So this is like some fake neutral axis that doesn't really exist in real life. And that's what this is, and that's what all these formulas are about. And yeah, so that's that. In the Eurocode, interestingly, A is just the name of a distance, right? So A is a distance. A1 and A2 in this particular formula is basically the distance from the neutral axis to the centroid of each shape, right? So they're just called A. That's the only difference in the Eurocode here. Again, then you have to find the effective stiffness, right? The effective stiffness is this formula, basically. And that's what you use when you put it into the deflection formula, I guess. Okay, so we're going to soldier on. We're about halfway through. The Eurocode is shit. It's so shit. But the upside to the Eurocode is it's easy to access. So if you Google Eurocode 5, you'll be brought instantly to a copy of the Timber Eurocode. So unlike the Australian Eurocode, the Australian standard is not like gate kept. It's super easy to access. The downside is it's like learning a new language, right? The Eurocode is fucking awful. Like, and it makes you really appreciate how easy and simple and straightforward the Australian load combinations and like how the code reads and everything is, right? So let's talk about how the Eurocode works, right? So you've got your loads, and they're split into kind of three broad categories. You've got your permanent actions, so that's dead load, like self weight and stuff. You've got variable actions, which is split into two subcategories. Split into two subcategories. You've got your live load, which is part of your variable actions, and your wind load, which is also variable. So when we say variable, it's time variable, right? So live load could happen for like 10 seconds, or it could happen for like 10 years or something, right? Like, you know, like a grand piano, you might leave it there for a day, or you might leave a grand piano in the same spot for like 10 years. So it's a time variable load. An accidental load, which we won't really focus on, but there's like a whole different set of load combinations for accidental actions in the Eurocode. Accidental actions include earthquakes, crash loads, if like a car like bumps into something, which it's not supposed to. What else? Those are the main ones, I think. Explosions. So explosions might happen when you have something like a substation, where it's a lot of electrical black magic and stuff's happening there, and overheats and could explode, right? So that's an explosion load. I should also mention that variable actions could also be snow. So if snow piles up in a certain spot, that counts as a variable. Yeah, anyway. What's that? Partial factors and load combinations. So, yeah, you have to understand two. So, again, like, forget what you know about the Australian standards for a second, and forget the fact that we're using gamma for something completely different to what we're just talking about with the gamma method, right? Gamma, in their equivalent of AS 1170.0, right? So their load combination code, they're talking about gamma as a partial factor constant, right? So essentially, for example, we have like 1.2G and 1.5Q, right? That would be like gamma, right? So that's like gamma G, and that's like gamma Q, okay? So gamma in their code is referring to the constant before a type of load, like a dead load or something, right? And so their equivalent for dead loads is 1.35G, right? And their equivalent of that 1.5 for Q is just 1.5, right? So it's, yeah, anyway, that's kind of how it works. There's a bit more to it than that. Like, this would just make it sound like all the loads are bigger in Europe, but like there's more to it than this, but just keep that in mind for now, right? Okay, the next thing you have to know is combination factors. So this is what I was talking about. So I think in our code, this is like your short-term, long-term combination factors for like serviceability, right? So that's short-term service load factor for Q, whatever. That's the long-term one, whatever. And that's something else for Q. That's for that like strength load case that involves wind and gravity acting in the same direction. Hello. Okay, forget everything you know about the Australian load combination for a second. The way that the European loads work is basically these go before this is the strength case, right? You've got your dead load, you've got your live load, right? And you have the gamma factors, which we talked about just a second ago. So that could be like 1.35, and that could be like 1.5, right? But now we have an additional one for each Q or each time variable load. So this could include wind as well, right? Now we also have a combination factor, right? And if it's phi 0, this means it's something called the leading load, I think, leading variable load, right? Okay, so I'll tell you what I mean. Right, so here's what I mean. So sorry, other way around. Sorry. Okay, not for the leading one. Okay, let's just talk about this, right? So you've got your leading variable load, and you've got the other ones. So if you have live load, sorry, if you have dead load and live load, your leading variable load is just live load, right? A different case, if you have dead load and you have wind load, your leading time variable load is wind load, okay? Now if you have all three of those, if you have dead load, wind, and live load, you have to check two sets of calculations, right? You have to check the case where live load is the leading time variable load, and you have to check when wind is the leading time variable load, and the other one takes like the back seat, I guess, right? Fuck, I really think that makes sense. So that that 0 is actually referring to in the short term. So we're doing the strength load combinations right now, and that's for when it's like a once-off worst case scenario. It's where like your wind is hitting and you've got like heaps of live load or like something like that, and it all happens within a very short period of time, right? So that's your short-term combination factor and why you need it for your other time variable loads. Okay, so and also like don't get too bogged down by the number of subscripts and shit happening here. Like I'll simplify it in the example I'll show you below. But K in the Eurocode means characteristic, right? That's like the definition. But we call it unfactored. So if you see something with K, this is unfactored. So it doesn't have like your exaggeration or under exaggeration factors applied to it. That's all it means. Okay, so here's an example of like a calculation involving dead load, live load, and wind. So you have to check for when live load is leading, and you have to check for when wind is leading as well, right? So when live load is leading, right, it's put in this spot, which is your leading time variable load, and you don't have to apply this reduction factor to it. And then wind, you apply the wind's reduction factor for when it's not the leading load. Fuck, does that make sense? In the short term. Fuck, there's like so much shit to say. So yeah, and then the second case, you've got wind leading now, okay? And live load's taking the back seat, but live load has a different factor than wind when it's taking the back seat, right? Can you get what I'm saying? So then you weigh up like these load combinations and you see which one's the worst one, and then this one would be the worst case, like strength load, right? Okay. I'm gonna check the chat, see if anyone's said anything. Oh no, all good. Yeah, if you have questions, just like send in the chat. Okay, so that was strength. Now we've got service, right? So service, we're dealing with 3 different load cases in service. We have short-term loads, frequent loads, and long-term loads. Now, frequent loads, I'm pretty sure, is fatigue loading, which in Australia is like a completely separate type of analysis. And you would do like a higher order analysis where you use like software rather than doing it as like a simple hand calc. But in Eurocode, frequent loading has its own combination, right? Okay. So here's where it gets a bit confusing. So sum, right? You know, like the sigma, capital Sigma, like sum symbol. When you do sum and you don't write anything, it just means like add everything together, right? When you have a sum and it says I is greater than K, what that's trying to say is greater than, in this case it means greater than 1, I think. So your leading one is the 1, and then you have like case 2, 3, 4, 5, etc. as like your sum, right? So what that means is like if you've got fucking live load, snow load, wind load, etc., right? Like you've got everything else as well, like everything that's not your leading case, right? But why I'm saying this, right, is because in the long-term case you have to be really careful, because in the long-term case you apply your combination factor. The long-term combination factor, so that 2 means long-term, right? You apply the long-term combination factor to the leading case as well, right? This will make so much more sense when you follow, like when you slowly work through this and try to do the question yourself, because it's just a jumble of numbers right now, and I won't be able to like teach it to you by explaining it, because you just need to do it and be like, okay, that's how it works. Because the European like code is like super trippy when you first look at it. But yeah, just trust me, it'll make sense when you do one question on it. Okay? Or you do your assignment on it, because I think you'll have to. Oh, but in the assignment, it's not as bad, because the assignment, I believe, is only dead load and live load. So you don't have to also check for live load leading and wind load leading, right? So in your assignment, it'll just be like one set of these, and like there won't be like this shit here as well. Anyway, it's still good to know though, because it might be in your exam. Okay, so strength design, everything also looks different, right? So in Aussie strength design, you just see this, right? You see your capacity reduction factor, and then the way that, and then your calculated resistance as per your standard and whatever action you're looking at, right? So for example, compressive strength of concrete or something like that. That's what that R stands for. But for Eurecode, it basically works the way that timber works. Because you know how like the timber standards, the Australian timber standards, looks really different to all the other standards because it has a bunch of K factors. Well, it's based on the Eurocode, and the Eurocode has a bunch of K factors for everything. And it's also got this one additional thing called the material factor. But yeah, well, okay, it's weird, right? Yeah, fuck. So our 5 factor, okay. Yeah, let me explain this slowly, because I'm starting to confuse myself. So in our standard, right, AS 1720.1 for timber, right, phi is a function of 2 things, right? It's a function of service class, or I should say like importance level or something like that, right? And it's a function of material, right? So if you recall that table, it's like you've got your I forgot exactly what it's called, like type 1, type 2, type 3, but it's like severity levels, right? So you've got like your really important buildings, like primary members in those buildings, so you got like your, you know, all that shit, like secondary members in like a residential house or something. It's like low importance, for example. So that's importance. And then it's also got material, so like it has a different 5 factor depending on if you're using like glulam or like plywood or something, right? So in the timber code, it's all captured, like these two things are captured together, right? Because this one's importance level, and this one is, you know, material. In AS 3600, in steels, right? So steels and concrete code, it's like importance level is not really captured. It's more material and action instead. It's a bit weird. So when I say action, right, I'm talking about tension, well, maybe tension, compression, bending, shear, right? It's about like what type of action is experiencing, and that'll like change what the 5 factor is, right? Yeah, anyway, I'll shut up now. So hopefully that makes sense. So that just captures the difference between how it works. But just think of it like the strength design is very similar to the timber code, right? It's just captured in 2 different factors. So you got this factor and you got this factor, and it's like as if you're reading off the different rows and different columns in the timber standards for the 5 factor value. Okay. K mod and gamma m. So K mod was your what's it called? It's like your modification factor, I guess, right? And that's the service class one. Oh, sorry, it's also got duration of load. It's kind of like, this one is like also a combination of K1 in timber, right? Yeah. So that's that. Oh fuck, am I trolling? Service class is not the same as the importance level thing I was talking about. Okay, sorry. It's not importance level. So K mod in the timber code is more like K1, K4, and K6 combined. Because K1 is that one there. Service class is actually K4, K6. So that's your temperature. So service class is something different to importance level. Service class is how the timber behaves in the presence of moisture and heat, basically. Sorry, I'm not terribly familiar with Eurocode, you have to forgive me. And then gamma m is, yeah, like a material correction factor, basically, right? And then here's the ones for when you're dealing with gravity and wind loads, and then there's a separate gamma m for like crash and earthquakes, accidental situations, right? Yeah, there's other K factors, so these are like additional K factors. Fuck, it's really dumb, right? Because like, I'm gonna open, let's just say like the compression material strength as like a small note. No. Yep. This shit, right? So, basically, if you recall, in the bloody, like, the appendix of the timber standards, right? There's like these random notes that are like, you could easily miss, but these are its own thing in, like, it's its own K factor basically in the Eurocode. Right. Oops. So the Eurocode has something called the size factor, which is basically just that. So it will adjust how strong your thing is based on, like, if it's too big, it's gonna reduce it or something, right? Anyway, the size factor is its own thing. Strength tables, these read pretty similarly to the Australian ones. I've highlighted the ones which you'll need later for how to, like, when you're doing your assignment. Actually, yeah, I think so. I think this one's for strength. And then these ones are kind of useful. This is for loads, and this one's for serviceability. Yeah, so you'll need these ones. Yeah. Connection design is formatted similarly, but like the wording's a bit different. You've got all these extra cases and notes and shit as well. You'll start to notice the quality of the notes decline as I keep going because I ran out of time. But yeah, so keep in mind, just like how K1 behaves differently in the Australian standards for connections and for members, they also behave differently for this table. So yeah, like, as in, like, there's different values for it, right? That's what I'm trying to say. So this is the K-mod table for connections, is different. And gamma M, your material factor is different as well for connections. Okay, moving on to design of TCC. So this is the last thing that I've got, and it just runs over the next few pages. We're doing serviceability design for a timber concrete composite slab and beam system, right? You have an effective width, right, which is basically just, it becomes like a T-beam because part of the slab is considered on both sides of the beam, and there's these, like, kind of formulas to calculate that effective width. So that's the first step. That's the first thing you have to find. It's worth noting that LC here is talking about the length. So if that's a bending moment diagram, right, it's the length between the points of zero bending moment, right? So if you have pin on both sides, it looks like that. But if you have, like, a point of inflection, it's that, right? And basically that second term is going to override B1 and B2 if you have too short of a span of between inflection points in your bending moment diagram. Yeah. Okay, step 2. You basically have to grab all your material properties from various sources. So for concrete, you go to AS3600 and you find this table, which I've just included here for you. So you need the mean compressive concrete strength, and you need the I can't think, elastic modulus of the concrete, right? For timber, you can go back 2 pages to when I have, like, all those characteristic properties for, like, glulam and structural timber and stuff. You grab those 4 values I talked about. Okay, and a key thing when we're doing, like, when we're converting density to unit weight, right? Because density and unit weight are different. Density is given in kilograms per meter cubed, but can't talk. Unit weight is in kilonewtons, right? So the way you get from kilograms to kilonewtons is you multiply by 10, right, which is just a rounded number for gravity, and then you divide by 1,000, right? So effectively you divide by 100. That's just like a rule of thumb. So think of it like, the way you can remember it is, like, imagine you have, like, a really it's not even that heavy, right? But you just, like, have, like, an average tradie bloke, and he's, like, 100 kilograms. Like, he weighs 100 kilograms, right? That's 1 kilonewton, right? So that tradie is 1 kilonewton. That's an easy way to remember how to convert it. Okay. Yeah. Step 3. You find the loads, and you can break it up into G and Q. So why I was talking about all that is because you have to find like the self-weight of the timber, self-weight of the concrete, which we're going to consider as 24 in this course, kilonewtons per meter cubed, and SDL. So SDL is like superimposed dead load. So if the question gives you a superimposed dead load, then multiply it by your by your flange width, because your SDL is like applied over there, right? And you multiply it by that, and you get your SDL in kilonewtons per meter. So if you multiply by your effective flange width, right? Yeah. Okay. And then Q, same thing as what I've drawn here, but instead of SDL, we're considering live load in kPa. You multiply it by that flange width, right? Okay. So I say here, go back 5 pages. What I mean by 5 pages is when we talked about the Eurocode load combinations for serviceability, if you want more details. But I've just included a copy of like the key things here. Okay, next step 4, creep coefficient for concrete and timber. So in the concrete code, the Australian one, the cool thing about this topic, and also like how new this research is none of it's consolidated into the Australian standards, or like parts of it are. So we're borrowing a little bit from the Australian standards, we're borrowing a little bit from the Eurocode. So whenever we do load combinations, it's from the Eurocode. Whenever we do timber related calculations, it's from the Eurocode. When we do like the shear studs, that's Eurocode. But when we do concrete related stuff, it's the Australian standards, right? So keep that in mind. Okay, terminology. Oh, like this is all part of the Australian standards, but like you don't really talk about this in regular concrete, but you talk about it in advanced concrete. Basically, there's a creep coefficient. What's that? Your creeping is like, so material will like deform so much in the long term, but creeping will basically be even longer term. So like over the period of like 10 to 30 years, right? It will keep deflecting. Like creep will cause you, the material creep of certain materials will cause your structure to keep deforming, right? And that applies to concrete, and that's this creep coefficient, and it also applies to timber, right? But it doesn't apply to steel, basically. Okay, so here's where I get lazy and just screenshot from the lecture slides, but this is from a worked example. Basically, why I say if it isn't given in the question is because in your assignment, it is given. So you can skip all this stuff. They just give you straight up, this is equal to some number. I think it's like 2.8 or something. Yeah. But here's how you would work it out. Otherwise, you have to like go into the Australian concrete code and you follow all the K factors, and those K factors are different to the timber standard K factors. So these are completely different. These are like creep related coefficients, right? So it's like you have a bunch of K factors and you multiply it by this basic concrete creeping constant. The light just turned off in my room. 1 sec. Okay. And yeah, that's all this shit. Okay, so Kdef is basically the creeping factor for timber, and it's located in the Eurocode. And basically, when we're considering the influence of partially composite timber concrete composites, we have to use this thing called K def dash, right? Which is literally just multiply by 2. Multiply whatever creep constant you had by 2. That's the rule. And then next we find the short-term stiffness. So this is the stiffness of, okay, basically, if this is our beam, each of these studs, sorry, that's concrete, right? And that's timber, right? And then these blue things are studs. Each of these studs has a certain stiffness, which you can calculate using that formula, right? You can calculate using that formula if you have some kind of dowel, like a bolt, screw, or nail, right? And you pre-drill it, which is the standard case. And then there's different cases and stuff on the slide. Okay. But if we want to find like if we want to find the connector stiffness along, like the average connector stiffness along the entire beam, right? We have to use this formula. And this value of your short-term stiffness per unit length along that beam is what the input is for the gamma method. So we're going to need to use it when we're when we're looking for the deflection, right? So yeah, it has like this thing which accounts for like how the studs are spaced along the beam, right? So just keep that in mind. I think in your assignment is cooked, right? Because just gonna draw it again. If that's your beam, your studs have a linearly increasing spacing. Like that, and then becomes more like that. So it linearly increases, so you have to find the average spacing, I believe, along the entire beam length. So yeah, good luck. I think that's an additional step. Yeah, gamma method for short-term values. Okay, so you apply the gamma method, which we talked about before. You can go up to this chapter of my notes, talking about the partially composite deflection, to rerun over the gamma method. And next step, and so that's just to find the short-term deflection, right? Sorry. Yeah, that's to find the short-term deflection. And next we have to, so this table is not officially in the Eurocode 5. This is like from a random excerpt somewhere else, right? So it's even more cooked. But we're trying to find the modification factor, which is not the same as the phi from the load combos. Yeah, so these are your this is a completely different value that we're going to multiply, that we're going to include for our long-term deflection and stuff like that, right? So first you have to check this, right, using these geometric properties, and if both those statements are true and in the correct range, then you're allowed to use this table, basically. And there's 3 inputs, right? There's time, there's your concrete creeping coefficient, and there's your timber deformation, like creep coefficient, basically. And then you can get 3 values out of it, right? You get phi, what's that, psi? I don't know. You get phi concrete, right? Your modification factor for concrete. You get your modification factor for timber, and you get your modification factor for connections, right? So those will change depending on time as well. And so, yeah, we're gonna need these basically. And you have to interpolate it if it's a number in between, right? So if it's 2.8, see an XY graph. So if we're 2.8 and the values they give you are for 2.5 and 3.5, you have to find whatever values you get, right, for this. Let's just say KDEF is 0.6. That and that, right? And then you have to interpolate and find that right value, right, for that case. Anyway, it's cooked, but like, you know what I'm saying? Like, that's what you have to do. Yeah, and then long-term stiffness per unit length has this completely different formula. But here's where you plug in the things we just found, right? And you basically find your long-term concrete elastic modulus, you find your long-term timber elastic modulus, your long-term service and ultimate stiffness, right? But we just need the one for service, right? So for deflections, you can find your stiffness, your long-term stiffness per unit length. And then you reapply the gamma method. You reapply the gamma method and you get this value, your effective flexural stiffness. And using that is how you get your long-term deflection, basically. And what's this thing? Instant long. Not sure what this is. Not sure what that is. And then your total deflection is that. And then I haven't even talked about the failure of concrete, like strength failure of timber concrete composites. So good luck. But I know it's to do with, it's very similar to AS3600 concrete, I believe. I say this purely speculatively from what I saw in the lecture slides, but there's going to be basically push and pull. You got your moments and stuff like that, and I don't know what you do with those moments, but yeah, I think this one is for probably, if I was to guess, this is the crushing of concrete. You got to check that moment, about that neutral axis there, and then this one is probably for crushing of timber. It's bending downwards. The top is in compression, so that's crushed timber. This one's probably the crushed concrete one you check. Tensile flexural failure is probably this. Of the timber. And yielding of the rebar. There. So that'll be that one. Steel. Let's do that. And check that that doesn't go over the limit. FSY. Failure of shear connections. I have no idea how you do that, but yeah. Probably shearing too much. Probably check the shear interface and probably deal with it similar to your type 1 connections. I don't know, I'm speculating, but yeah, there's probably a bunch of checks to do with that. And you would follow the European strength load combos, which are these ones. So you would use this one for that. Cool. just want to. I'm so paranoid of writing on my master set of notes. Okay, so that's that. I might have a question. I might have gotten a question. Oh no. Gonna check Discord on my phone. Okay, if there's no questions, thank you for joining. That will be the last session that I record, and yeah, good luck for the rest of this course.